Thank you very much. Hello, everyone. I want to also give a big shout out to the organizers of this conference, because when I saw the list of participants, I was immediately thrilled to meet all these people whose names I knew, but now get the chance to talk to, so that's very nice. So the result I present is joint work with Sofia Brenner, Jean Cardinal, Thomas McConville, and my former student Arturo Merino. So this talk has several perspectives. It has an algorithmic perspective, a geometric perspective, and also an order theoretic perspective. And I want to start with the algorithmic perspective. So the algorithmic perspective is that we set ourselves this task to exhaustively list a family of combinatorial objects. So for example, let's say we want to list all the binary trees with a fixed number of nodes. Or maybe we want to list all permutations of some ground set. Or as a third example, we may be interested in listing binary strings of some fixed length. And as a fourth example, I want to mention spanning trees. So imagine you have a fixed graph and you want to list all of its spanning trees. And you want to do this with an efficient algorithm. This kind of algorithmic question of exhaustively enumerating combinatorial objects, this is covered in depth, for example, in this book of Donald Knuth, The Art of Computer Programming. So it's a very fundamental task that people care about. So one important notion in this context is the notion of a gray code. So remember, our goal is to have an efficient algorithm, to list the objects as efficiently as possible. And of course, if we want to do this, a good idea is probably to list them in a way that we don't have to change the objects a lot when we go from one to the next. So we want to have every change very small. Yeah, because the ultimate goal is to hope for an algorithm that achieves the listing in constant time per new object. So this is the holy grail, so to say. And if we want to do this, then we can only do this if the consecutive objects in the listing differ by a small change. Yeah? So a local change, which depends on the objects. And such a listing of objects subject to a small change condition, this is what we will call a gray code. So there's a lot of results in this area. I'll mention four of these for these four classes of objects that I had on the first slide. So it is well known that you can list all binary trees with n nodes in such a way that you always go from one to the next only by one tree rotation. So this is a known result from the 90s. For permutations, you can list all of them by applying an adjacent transposition in each step. And this is the famous Steinhaus-Johnson-Trotter algorithm, which I will talk about more in the coming slides. We can list binary strings of length n in such a way that we only flip a single bit at a time. This is the so-called binary reflected gray code, a very, very classical result. Actually, this is the reason why we call these things gray codes, because there was a physicist called Gray, and this is why we call these things gray code. Yeah, so it's not the color gray, but it's this name, Frank Gray. And for spanning trees, it's known that we can list all spanning trees of any fixed graph by edge exchanges. So we go from one spanning tree to the next by removing one edge and inserting another edge. And these are all known results. So this notion of a gray code gives rise to another notion, namely the notion of a flip graph. So the flip graph has as vertices the combinatorial objects that we want to list, and it has as edges the pairs of objects that differ in these small changes. Yeah, so for example, if you look at binary trees with 4 nodes and edges being tree rotations, then we get this flip graph, which is, of course, an old friend, namely the associahedron. Here we take permutations of length 4 and we take edges between those pairs that differ in an adjacent transposition. Then we get this graph, which is, of course, the permutahedron. And here we have the hypercube, which comes from binary strings where the operation is you flip a single bit. And the fourth one is, of course, the flip graph of spanning trees, where here the underlying graph is a K4, and the vertices are the spanning trees, and edges are these edge exchanges. Yeah, so as you see already here from these pictures, these flip graphs have a lot of structure, a lot of symmetry. which we will want to exploit for this task of enumeration. Because these flip graphs can be realized, as we know or will see, as polytopes, and they often have the structure of posets and lattices and so on. Right, so these things are known, right? The isosahedron is the corresponding polytope, and the underlying poset is the Tamari lattice. Here, the underlying poset is the weak order, and the polytope is the permutahedron. Here we have the hypercube and the Boolean lattice, and here we have the base polytope. I'm not aware of any underlying order here, but that's the polytope. Yeah, it's a 0-1 polytope. Of course, when we want to do exhaustive generation in the gray code order, then what this means is we want to walk through this flip graph and traverse a Hamiltonian path or cycle. Yeah, we want to visit every vertex exactly once. This is a Hamiltonian path, and then if we also want to go back to where we started, then this will be a Hamiltonian cycle. And by these four aforementioned results, all of these flip graphs have Hamiltonian cycles. So these are classical results. Okay, so let me talk a bit more about this Steinhaus-Johnson-Trotter algorithm, because it is at the heart of much of what I will say in the following. So the Steinhaus-Johnson-Trotter algorithm is a particular way to list permutations by adjacent transpositions. And there's different ways how you can define this. I'll show you two of these ways, and then we'll see what we can do with this. So geometrically, as I said, this algorithm produces a Hamiltonian cycle on the permutahedron. And these listings that you see on the right-hand side are these lists of permutations along the cycle for 2, 3, and 4 symbols. And the definition that you see here is inductive. So what you do is you take the listing for some length n, and in order to create the listing for the next larger value of n, you take each of these smaller permutations and you insert the new symbol n in all possible places. And you do this insertion alternatingly from left to right and from right to left. Yeah, this is what happens here. So for example, this first permutation here gives rise to these first 3 permutations in the next list, where you insert the 3 in the right, middle, or left place. And then you always do this alternatingly in the opposite direction, and you get this picture, and this largest symbol performs this kind of zigzag movement here. So this is a term that I will frequently use in the following to remind you of this algorithm, where somehow the largest symbol performs this movement most of the time. Yeah, and then the next larger symbol performs the movement with the second largest number of times, and so on. And the 2 moves the least number of times, and the 1 never moves. Yeah, so this is this notion of a zigzag construction. So this is an inductive way to define this particular gray code. It's very straightforward. You can easily convince yourselves, yes, these are adjacent transpositions, and yes, everything is in our list exactly once. That's very easy. There's another definition of this ordering, which is not inductive, but uses an algorithm. And I will try to show you what this is, because I think it's kind of neat, and it's another way to understand the same construction, but through a different lens. And this is this Greek algorithm due to Aaron Williams. So the algorithmic description is as follows. You start the listing with the identity permutation, and then there's a simple rule how you move from the last permutation to the next one. And the rule tells you which transposition to apply. And the rule is the following. It says you look at the last permutation in the list, and then you try to do a transposition with the largest possible symbol so that you get a new permutation, one that you don't have yet in your list. And this is what you do. Yeah. So let's maybe try. Okay. Try to do this. Just to illustrate how this works in this case. Trying not to touch this cable here. Okay, so this is our initial permutation. Now the rule says try to swap the largest possible symbol. So this would be the 4. The 4 cannot move to the right, so it can only swap with the 3. So this is what we do, because this is a new permutation here. We haven't seen this one yet. Okay. Now we look here, we look for the largest possible symbol. Can we swap it to the right? No, because this is a permutation we have already. Can we swap it to the left? Yes, this is something new. So this is what. Okay, so we look here. We look for the largest possible symbol, which is the 4. Can we swap it right? No, because this we have already. Can we swap it left? Yes, this is something new. So this is what we do. Okay, so now we look here. The largest possible symbol, can it swap to the right? No. Can it swap to the left? No. So we look at the next largest one, which is the 3. And the 3 can move to the left. And then we do this. And so on. And then at this stage, the 4 starts moving again, and so on. Okay? I think I should just not move at all. Moving is very risky here. Okay, so is the algorithm clear? Okay. So this gives, you can easily convince yourself that this gives the same listing as the one that I described inductively. This greedy algorithm was somehow the basis of a series of papers in which we somehow exploited the full power of this seemingly simple approach. And this led to what we call the zigzag language framework. So it's a somehow framework to generate any set of combinatorial objects by encoding them as permutations, then running this simple greedy algorithm, and then getting a listing for the objects that is hopefully a gray code. And this was very, this can be seen as a generalization of this Steinhaus-Johnson-Trotter algorithm. And we did use it successfully to generate many different combinatorial objects, and I will just mention some examples here. So it works very well to generate pattern-avoiding permutations, for example, Catalan type permutations, also Baxter permutations, and many others. We also use it to generate pattern-avoiding rectangulations, including diagonal rectangulations, generic rectangulations, and many others. You can also use it to generate binary trees, also pattern-avoiding. Then, maybe slightly more relevant for this community, we also applied it to generate lattice quotients, so Hamiltonian paths and cycles in the cover graphs of these lattice quotients arising from the weak order on permutations, which in particular implies Hamiltonicity of certain quotientopes. I'll talk about more of this in the next slides. And we also used it to generate elimination trees of caudal graphs, which implies Hamiltonicity of certain graph associahedra. And most recently also we applied it to generate acyclic orientations of caudal graphs and hypergraphs and the corresponding lattice quotients. I will say a few more things about some of these points. You don't need to understand everything, but the point is here that somehow this simple greedy strategy can be generalized and is very powerful and applies in many settings. Yeah. And in this work, we will try to somehow push this principle a bit further and provide a framework or a viewpoint that unifies and generalizes many of the results that you've seen on the previous slide. And so it has the advantage that it's more powerful, and it has the additional advantage that it also simplifies many of the previous proofs. So the results get more powerful, but the proofs at the same time get simpler. So we win on both dimensions somehow. And the setting that we look at is the setting of hyperplane arrangements. Yeah, so we have a set H of hyperplanes. We assume that these are all central hyperplanes, so they all go through the origin. It's a non-empty set. They live in some high dimensional space, R to the n. And this is the set H. Then we look at the so-called graph of regions. So we look at the set Rn minus the hyperplane. So you remove the hyperplanes. So what is left are these cones, these maximal connected pieces. This is what we call the regions. So this is what we denote by R of H, the regions formed by this arrangement. These are the, and on top of this we define this graph G of H. So this graph G of H has those regions as vertices, and it has an edge between two regions if and only if they differ or separated by exactly one hyperplane, as you would imagine. So here's an example. If you take the 3 coordinate hyperplanes in R to the 3, it looks like this. You will have 8 regions, and so the graph will have 8 vertices. The graph is shown here, and in this particular case, the regions can be identified with binary strings, and walking through a hyperplane corresponds to flipping one of the bits in the strings. So this is one example of such a graph of regions. I will, in the following, often show these kind of pictures. So these are, again, stereographic projections of some 3-dimensional arrangement. So we have an arrangement in R3. We intersect it with a sphere. So we get these great circles on the sphere. And then we project these great circles onto the plane to get these pictures that are somehow more easy to understand for a human brain. And also take less time to draw when you want to make these drawings. Okay, so this is the graph of regions. Yeah, you can define it for any set of hyperplanes in any dimension. And our goal is, of course, to find a Hamiltonian path or cycle in this graph. Maybe in some cases figure out that there's no such path or cycle, but if it exists, we also want to find it efficiently or understand its structure. This is the goal. Let me go through some examples of arrangements that we will encounter frequently in the following. So the first one is this maybe most basic kind of arrangement you can imagine, namely the arrangement where you put as normal vectors all the unit vectors. Yeah, so these are the coordinate hyperplanes. And the arrangement that you get is what you see here. And this is one example of the corresponding graph of regions. Another one we'll frequently use is this braid arrangement. So you have a parameter n, and you take all pairs of numbers I and j smaller than n, and you put in this hyperplane with normal vector ei minus ej. This is also referred to as type A Coxeter arrangement. The corresponding type B Coxeter arrangement is also there, and it looks as follows. You put all hyperplanes with normal vectors ei minus ej, and ei plus ej, plus also the coordinate hyperplanes. And here's how it looks in 3D. Here's the corresponding graph of regions. Let me maybe go back to this picture. So here in the type A Coxeter arrangement, the regions can be identified by permutations, and going through a region corresponds to an adjacent transposition. Yeah. And similarly here for the type B, the regions can be identified with signed permutations. So every symbol of the permutation has a plus or minus sign. And then there's 2 types of flips. So either you do an adjacent transposition or you change the sign of the first entry. These are the 2 possible flips that arise from this. And what else do we have? We have the graphic arrangement. So here there's an underlying graph f, fixed graph f. And this graph f defines which hyperplanes we take from this braid arrangement. So it's a sub-arrangement of the braid arrangement. You don't take all those differences here, but only those that correspond to edges in the graph. Yeah? So if you take the complete graph, you get the braid arrangement. If you take something else, you get something smaller. You get an arrangement with fewer hyperplanes. I think I should stick it like this. Okay. Let's look at some basic properties of this graph of regions. So some things we can directly see when looking at this definition. So one is that the number of regions is always even. This you can easily see by looking at this opposition map. So every vector x you map to its complement minus x. This maps every region to another region and back. So that's an involution between pairs of regions. And this shows that the number of regions is even for any arrangement, any central hyperplane arrangement. This graph of regions is also always bipartite. This is true even for any kind of arrangement, not necessarily central. So this means that you can color the regions black and white, and whenever you cross a hyperplane, the color changes. And the proof is very easy by induction, right? So you have an arrangement, it's bipartite, you add a new hyperplane, you just swap the colors on one side, and this way you get a bipartition for everything. So this is the corresponding picture here. Okay, so the graph is always bipartite, in particular for central hyperplane arrangements. Another observation is that if the number of hyperplanes is odd, then this bipartite graph has two partition classes of the same size. So this is this notion of balance. So balance means the two partition classes have the same size. So there's the same number of black regions as white regions. Because you can observe that in this case, the opposition map always changes the color. So you get an involution between white and black guys. Yeah. The reason why we care about this balancedness is because it's a necessary condition for Hamiltonicity. If we want a Hamilton cycle in a bipartite graph, then the two partition classes have to have the same size. Otherwise, we cannot possibly hope to find a cycle. So then we would be immediately screwed. Yeah, so if it's unbalanced, then clearly there's no cycle. And if it's balanced, there is a chance that there may be a cycle. And balancedness is, of course, not sufficient for Hamiltonicity, even in R⁻³. So here's an example of 7 hyperplanes in R3 with the corresponding stereographic projection. So this is an odd number. It's 7 of them. So I know already there will be the same number of black and white vertices in this graph of region. And still, it is not Hamiltonian. Yeah, Hamiltonicity is not. It doesn't follow from balancedness. So maybe for the people who are interested in great circle arrangements, so these graphs that we are looking at here in R3 are dual graphs of great circle arrangements. Yeah. And there's a lot of interesting questions you can ask only about this subclass. Okay, so now let's talk a little bit about the poset side. So we can take this graph of regions and turn it into a poset by making one of the regions the minimum element and orienting all edges away from this base region, or in said differently, we can sort the vertices by distance from this base region. This defines a partially ordered set. This is what we will call this pH of R0, so the poset associated with its hyperplane arrangement H, if I choose R0 as my base region. And why does it give a graded poset? Why are there no edges between a level? Because the graph is bipartite. Yeah, so there can't be edges between levels because this will be an odd cycle. And we know it's not. It has only even cycles. Okay, so we get a graded poset. And sometimes we get a lattice, but this requires some extra assumptions, as I will talk more later what these will be. So, for example, if we do this for the coordinate arrangement, of course, we get the Boolean lattice. And for the type A Coxeter arrangement, we get the type A weak order. So here, permutations with the identity at the bottom, and then the reverse identity at the top. For the type B, we get the corresponding type B weak order. So we get signed, I don't have a picture for that, so it's slightly bigger. So we have signed permutations, and the operations are adjacent transpositions or changing the sign of the first entry. But it's a similar picture, but quite a bit bigger. For the case where H is a graphic arrangement, we get something that is called the acyclic reorientation poset. So the regions of this arrangement are in bijection with acyclic orientations of the graph. And the base region is somehow the base orientation. And then going up means you flip one arc in the acyclic orientation. And the top will be all arcs being reversed compared to the base orientation. This is something that Pilaud introduced, and studied and also proved when is it a lattice and so on. So this is well understood. And of course, in those cases where this poset is a lattice, then we can play the whole game of lattice congruences and their quotients and ask ourselves, do these quotients also have Hamiltonian paths and cycles and so on? So for example, here on this type A weak order, if we contract these pairs, so the bold black edges are pairs of permutations that are in the same congruence class. If we take the corresponding quotient, we get this quotient, which is of course the Tamari lattice in this case, with the corresponding combinatorial objects being binary trees or corresponding triangulations. Okay. Now this was the poset perspective, and now what's the geometric perspective? So the polytopes that are associated to these objects. For such a hyperplane arrangement H, we can take the Minkowski sum of all the line segments in the directions of the normal vectors of these hyperplanes. This gives a polytope, this zonotope C of H. And we can look at its normal fan. And it turns out that the skeleton of the polytope is exactly isomorphic to the graph of regions. Yeah, so when we are traversing this graph of regions, we are walking on the skeleton of the zonotope, traversing the skeleton of the zonotope. So these are these pictures that I had already on my slides. So for this arrangement, the corresponding zonotope is the hypercube. And here it's the permutahedron for the type A Coxeter arrangement, and for the type B, it's the B permutahedron. Yeah. Okay, and now let's look. In the fourth case of graphic arrangements, we get what is called the graphic zonotope. Yeah, so you take a graph, you take and for every edge, you take the corresponding hyperplane. So this is called the graphic zonotope. And of course, you can ask yourself, okay, what about polytopes when I do this quotienting? So if I look at these lattice congruences, you can think about that what they do is they collapse or glue together these regions that belong to the same equivalence class. And this makes this fan smaller. It glues together certain cones. And you can ask yourself, okay, so I get this quotient fan. So this is what you see here at the bottom. Originally, there were more hyperplanes here, which somehow have disappeared because these two pieces here have been glued together to one. And you can ask yourself, is this quotient fan, is this the more normal fan of a polytope? And this was answered affirmatively, of course, by Pilaud and Santos, who constructed geometric realizations of these objects. This is what you can see here. So the red polytope is the polytope for the full braid arrangement, and by removing certain hyperplanes, you get this blue polytope, which is the associahedron, the classical associahedron, which is whose normal fan is this quotient fan. Yeah. And these polytopes are known as quotientopes. Yeah. Type A quotientopes, we should say more precisely, because here we started with the type A Coxeter arrangement. And this includes, already this class is huge and includes many interesting polytopes that we care about, such as the classical associahedron, permutrihedra that we heard about, also rectangulotopes, so where the vertices are rectangulations, hypercubes, of course, and many others. If you look at the type B Coxeter arrangement, you can ask the same question. Okay, I do this quotienting on the fan. Is the result a normal fan of some polytope? And Padrol, Pilaud, and Ritter proved yes, that there is this geometric realization of those as polytopes, and they call these type B quotientopes. So here you see again such an example. The red one is the type B permutahedron, which you get for the full arrangement. And once you do this quotienting, what you do here is you shift out certain hyperplanes, and you get, in this case, you get the type B isosahedron. Yeah, so this blue one is the type B isosahedron in this particular case. This has been studied on its own. Yeah. Okay, so in this talk, we will focus specifically on a certain type of arrangement, and these are called supersolvable arrangements. So let me tell you this notion. This is something that was first defined in the context of group theory. So, and later translated somehow to a lattice theoretic language. And what we will use here as a definition, instead of these original definitions, we will use a characterization that appears in this paper of Björner, Edelman, and Ziegler. And we will use this definition as a starting point for everything that comes later, because it is the most convenient for what we want to do, as you will see in a moment. Okay, so here's our definition of supersolvable arrangement. So this H is the full arrangement, and there's two cases. We look at its rank. So the rank is the dimension of the space spanned by the normal vectors of the hyperplanes. If it's trivial, so if the rank is 1 or 2, then it's always supersolvable. So any arrangement of rank 1 or 2 is supersolvable. There's no condition. And if the rank is at least 3, then we require the following. We require that you can split the hyperplanes into two sets, H0 and H1, such that some conditions hold. So what are the conditions? So in this picture, the splitting is what you see here. So this is the full arrangement. And now the ones in H0, they have become blue, and the ones in H1, they have become red. And what are the conditions? The conditions are that H0 should again be supersolvable and should have smaller rank. Yes, so H0 should be supersolvable and have one rank smaller than the full arrangement. And H1 should be what? Well, it should be the following, that if I take any two hyperplanes from H1 and look at their intersection, then the intersection should be contained in one of the H0 guys. Okay, so let me show you in this picture what it means. So let's take two hyperplanes from H1. Let's take these two red guys. What is their intersection? Intersection is just this point and this point. And the condition says these 2 points must be contained in one of the blue hyperplanes, which they are in this case, namely they are contained in this blue hyperplane. Okay, so and now you check this for any pair of two red guys. They must be contained, their intersection must be contained in a blue. And in this picture, it's true. Yeah, that's the definition. Is the definition clear, or should I expand on it? Okay. It turns out that these examples of arrangements that I talked about before, they are all supersolvable. Well, not all of them, but most of them. In particular, the coordinate arrangement and the type A and type B Coxeter arrangements. For the graphic arrangements, there are some conditions on the graph, which I will talk about in a moment. Let's come to our first result. So that's our first main theorem. It says that if you have an arrangement that is supersolvable, then the graph of regions has a Hamiltonian cycle. Yeah, so it's a sufficient condition for this graph of regions to admit a Hamiltonian cycle. I should say that this result was also independently obtained by these authors, Körber, Schnieders, Stricker, and Valisade. Now we can ask the next question. Okay, now the graph of regions is Hamiltonian. What about the poset and the lattice and the congruences on top of this lattice? Well, for this we first need to understand when is this poset of regions a lattice. For this, we look again into this Björner, Edelman, Ziegler paper. They tell us that if the arrangement is supersolvable, then there is a base region that you can choose so that you get a lattice. And in fact, well, it's not just an existential result. They tell you what you need to choose as a base region. You cannot choose every base region, but there is a way to choose it. There's actually many ways that you can choose it. I will not define exactly how to choose it, but you can trust me that there's a way to choose it. And the choices that work is what they call canonical regions. So you can define what canonical means, but I don't do it because for us it's enough to know that if you choose a canonical region, then this poset is a lattice. Yeah? So that's enough for us to know. Okay, so we can choose a region, canonical region, we get a lattice. Okay, now what about the congruences on top of that lattice? This is our second main result. If you have any supersolvable arrangement and you choose any canonical base region, R0, now you look at this poset of regions, which in this case is a lattice, and you look at any lattice congruence on top of it, and you look at its quotient, so this is the quotient here, L modulo the congruence, and at the cover graph of this quotient, so it's again a lattice, and you look at the cover graph, then in this cover graph, you can traverse a Hamiltonian path. Okay, so this is a generalization, of course, of the first term. However, there's a slight cost here. It's only a path, whereas here it's a cycle. So in some cases, this can be strengthened here, but this general theorem only guarantees a path. So these are the two main theorems. In the following, I want to talk a bit about applications, like consequences of these. Yes, there's a question.
For this path, you have a special starting point. Do you start from the bottom, or?
One way to start would be to start at the canonical base region. Yes, this would be the bottom. Yes, this would be one choice. There's other choices that work, but this is one choice. Yes. There's another question. I don't know an example where it's impossible to have a cycle, but I know examples where our construction only gives a path and not a cycle. Yeah. Okay. Yes?
So both theorems, do you know how many Hamiltonian cycles?
There is freedom in these results. So for example, when you do this construction, there are like some degrees of freedom, and if you exploit this freedom in every step, you not just get one cycle, but you get many cycles. And the same is true for this bottom thing. So there are some choices that you can make, and if you do it, you get many solutions. But we never tried to count them. But no, I don't think so. I don't think so. I mean, one could try some asymptotic estimate. It will be a huge number. But maybe there are much more even, yeah. Okay, other questions? Yeah, okay, feel free to ask if there's more coming up. So, yes, as I said, I want to talk about applications now, like what are corollaries and implications of these somehow general results. So what I will do, I'll just take these arrangements that I talked about in the beginning and throw this hammer on each of them and see what comes out, right? Okay, so let's look at the coordinate arrangement. It turns out, of course, that the corresponding cycle that we get is this old friend of us. It's the binary reflected gray code. Yeah? This is a known result, of course. Nobody is surprised that this comes out here, but it's a very, very special case of this general theorem somehow. If we do this for the type A Coxeter arrangement, of course, the cycle that we get is the well-known ordering that comes from the Steinhaus-Johnson-Trotter. Also something that we know. So we recover also this as a special case. Here's something new. If we do for the type B Coxeter arrangement, we also get a Hamiltonian cycle. So a listing of sign permutations, where in every step we either do an adjacent transposition or a change of the first sign of the first entry. And this is something that apparently is new, that was not known. So it gives a new gray code for sign permutations and the corresponding, so this would be the listing, and the corresponding cycle here is what you see here. So at the top and bottom, these two blue facets are these smaller dimensional permutahedron, and this red cycle zigzags back and forth between these top and bottom facets. Yeah? So it's this zigzagging idea behind this picture. This algorithm can also be implemented efficiently if you care about this. So it can be implemented in constant time per permutation, and we call this a loopless algorithm. What about the graphic arrangement? As I said, it's a sub-arrangement of the type A Coxeter arrangement. We need to first understand when is it supersolvable. Yeah? This was done by Stanley in the 70s. He showed that this arrangement is supersolvable if and only if the graph is caudal. This is very nice. So that means that if the graph is caudal, we can take this arrangement, apply our result, and get gray codes for acyclic orientations of caudal graphs. Yeah, so it's not for all graphs, but only for caudal graphs. It is known that this graph association is Hamiltonian for any graph. This was proved by Vincent and one of his students. But here we recover it for caudal graphs, which also is something that we did in an earlier paper, but now we have it from this more general point of view. You can also do it for these quotients of these acyclic reorientation lattices. This is also something that was known, but it also comes out from this theorems as a special case. Now, here's again something new. There's something called the signed graphic arrangement. So this is somehow the analog of graphic arrangements, but for the type B setting. So we start with a type B Coxeter arrangement, and we take a sub-arrangement. And the sub-arrangement, so which hyperplanes we take, is specified by a so-called signed graph. So in a signed graph, the edges have signs. So every edge is either a plus or minus edge. And those edges you can think about, yeah, and those edges define which hyperplanes you take. And again, we ask, like, when is it supersolvable? So when can we use our results? This work was done for us by Zaslavsky in the 80s. So he introduced this notion of acyclic orientations of signed graphs. So you can, again, identify the regions of the arrangements with acyclic orientations of these signed graphs. And so there's a bijection between the regions and acyclic orientations of signed graphs. I don't define here exactly what are these acyclic orientations of signed graphs. So what does it mean to have a cycle in a signed graph? I don't show these things, but there's a way to define it. And yeah, that's enough, I think, for this talk. Okay, and there's also an analog notion of caudality. So remember, in the unsigned setting, the arrangement was supersolvable if the graph is caudal. Something like this is also true here. The way it's stated here as this theorem of Sadlavsky is an implication that's saying that if this graph admits something that is called a signed perfect elimination ordering, then the arrangement is supersolvable. So again, I don't say what this signed perfect elimination ordering is, but it's an analog of these perfect elimination orderings in graphs, which are these caudal graphs. Yeah? So in a perfect elimination ordering, you eliminate vertices in a way that when you remove something, a vertex in its neighborhood must be a clique. Yeah? And there's something similar here for signed graphs, and then this arrangement is supersolvable. Actually, Zaslavsky proved an if and only if statement, but this other direction has some exceptions, so this is why I skipped this exception and only wrote one implication of the theorem here, because these exceptions are just annoying and we don't care about them. We only care about supersolvable. Okay, so as a corollary from our main theorem, we get that if the signed graph indeed has such a signed perfect elimination ordering, then the corresponding polytope, so the corresponding signed graphic sonotope, has a Hamiltonian cycle. Yeah, this is a consequence of the first main theorem. And this way we obtain also gray codes for the quotients. So on these guys, again, we can do quotients. So we get listings of equivalence classes of lattice congruences on these acyclic reorientation lattices of signed graphs. I don't think there's a known polytopal realization, so It's an abstract result, but once somebody proves that there's a polytope, then we know already that this polytope has a Hamiltonian path. Is there a question? No. Here's another application. So now I want to go into this quotienting applications, and I want to do first quotienting on these type A Coxeter arrangements. So the corresponding polytopes, as I mentioned, are the type A quotientopes. They were first defined by Pilaud and Santos. And in earlier work, we proved already that they have always a Hamiltonian path. It's not known whether they always have a Hamiltonian cycle. This is open. We proved that they have a path. And these are, again, already this class of objects is a generalization of many known gray codes, in particular the gray codes for trees by tree rotations that were discovered in the 90s that I mentioned in the very beginning. So all these are special cases, also Hamiltonian paths for these so-called rectangulotopes. These are all special, arise all from special lattice congruences on the weak order of type A. So what I show you here is a gray code that follows from our work, a gray code for diagonal rectangulations. Yeah, so here you have a subdivision of a rectangle into 4 smaller rectangles such that there's such that all crossings are T's, yeah, but no crossings like this, only T's. And every rectangle intersects the black diagonal. And there's a notion of flip here that allows you to go through these guys one after the other, and then after this one you have to go here, and then you go here, and after this one you can go back to the first one. Yeah, so it's a cyclic gray code. This was also discovered earlier, but it's again a special case of somehow this more general viewpoint. Now here's something new again, namely if we do quotienting on these type B arrangements, so type B Coxeter arrangements. I told you already that there's corresponding polytopes, namely these type B quotientopes that were introduced by Padrol, Pilaud, and Ritter. And we get as a corollary something new, which was not known, namely that these polytopes all have a Hamiltonian path. Yeah. I also think it's not known whether they have a cycle. They may have, but it's not known. And as a special case of this, of course, we can also get concrete gray codes, for example, for the B isosahedron. Yeah? The B isosahedron, which you see in this picture here, has as vertices symmetric triangulations. So you have an even number of points in convex position. You look at triangulations that are point symmetric with respect to the center. And the flip operation now is either you flip this line through the center, or you flip a pair of edges that are symmetric with respect to the middle, to the center point. And as a consequence of this, here's a gray code. So this bold red lines here, they indicate a Hamiltonian cycle in this case. So the corollary just says path, but in this particular case, it turns out that it's always a cycle. So it's not really a corollary, but if you look more closely into the, it's actually a cycle. Let me show you the proof of theorem 1, because I claimed it's somehow very straightforward and easy, so I will show you the full proof. Okay, so what's the theorem again? We have a central hyperplane arrangement H. We assume that it's supersolvable, and we claim that the graph of regions has a Hamiltonian cycle. Okay, so how do we prove this? Well, we start with this partition that is used in this definition of supersolvable, right? So supersolvable meant, okay, we can split the hyperplanes into 2 sets, H0 and H1. This is what you see in this picture, such that some conditions hold. So let me remind you of the conditions. The conditions were that H0 is an arrangement of smaller rank that is also supersolvable. So that's nice, because then we know by induction that there is already a Hamiltonian cycle for this graph of regions in the smaller arrangement, right? So this is what you see here. The blue arrangement has smaller rank. It is supersolvable. And its graph of regions has a Hamiltonian cycle. So this is something that we will use by induction. But let's forget about this for the moment. Let's look at the other condition. What is the other condition? The other condition says whenever you have two hyperplanes from H1, and you look at their intersection, then this should be contained in one of the blue hyperplanes of H0, right? And this is the property that will be crucial now for the proof. So what we'll do is we'll look at this map rho. And what is this map? This map maps the regions of the full arrangement. This is the pyramid. It maps it to regions of the sub-arrangement H0. And what it does is it maps the small regions to the bigger region that it is contained in. So this is the mapping. So for example, if you look at this little region here, it will be mapped to this blue region of H0. And similarly, this little region in red will be mapped to this big blue region in H0. And this is true for this one also. And the key observation is that if you look at the fiber, so if you look at which guys, small guys are mapped to the same big blue region in H0, that this is a path in the graph. So if I look at all these little red guys that map to the same blue guy, let me go back and forth. All these guys, they form a path in this graph of regions. Yeah, so they are linearly ordered. I can traverse them one after the other and pick up each guy along the way in this region of H0. Yeah? And now you can probably already guess what the proof will look like, because this applies now to every of these regions of H0. Yeah? Each of these regions, there's this path. These paths all have the same length, and the length is given by the number of hyperplanes in H1. And now it's clear what we do. Yeah? So now we do induction. By induction, we know that the smaller arrangement has a Hamiltonian cycle. So we take two copies of it, one being very close to the origin and one being very far from the origin. These are these two copies. And now, well, we put back those paths between these two. And now you remove every second edge on the inside and every other edge on the outside. And then you get your Hamiltonian path. Yeah? Okay, why is it a Hamiltonian cycle? Hamiltonian cycle. Why is it a Hamiltonian cycle? Because the number of regions is even. Yeah? This is true for any arrangement, in particular for this H0 arrangement. The number of regions is even, so this means when you go back and forth, you come back to where you started. Yeah? So you get the Hamiltonian cycle. And that's the proof. Yeah? This is the end of the proof, and yeah, it's also the end of the talk. So thank you very much.
Thanks, Torsten, for this very nice talk. Question time. We have a few minutes, but before you ask your question, be sure to get the mic first. Otherwise, we don't hear you. Okay? Any question?
Thanks for the talk. Is there an extension of the notion of supersolvability to orienting matroids and to the graph of top of orienting matroids?
Probably yes, but I don't know the answer. Maybe some other people in this room know the answer.
I'm pretty sure the answer is yes, but
yes,
some people in the room know better.
The same proof works.
The same proof works for Hamiltonicity.
Okay, good.
Any other question?
In the very back, yes.
Yeah, thank you for the talk. Besides Hamiltonicity, have you and co-authors look at like other graph theoretic properties of these couple graphs?
Of which graphs?
Like as
of
in like, of the
regions.
lattices and or like their
regions.
Hasse diagrams.
I mean, one thing it was brought up today at some point was the question, when are these graphs regular? So when do all vertices have the same degree? So this is something that we understand, for example, for the weak type A quotientopes. There's some simple combinatorial condition when they are. Other questions that people care about are, of course, diameter, like what is the diameter of these graphs? This is known for some special cases, but sometimes even that very hard to prove anything. Yeah, these are typical things that people care about, yes. Okay. Or symmetries, like Vertex transitive, like when are they highly symmetric, like permutahedron and hypercube are vertex transitive, right? So that's a very strong notion of symmetry. We also know when these quotientopes are vertex transitives, for example. Yeah.
Yeah, thank you.
Any other question?
Connectivity is something that people care about a lot. Like how highly connected are these graphs? This is known for some of these.
I just had a question about the memory efficiency of the algorithm, because it's when you first talked about the algorithm to go through permutations, it seemed like the greedy algorithm was not efficient for memory.
That's
You
right.
had to remember the list of everything you've done.
That's right. That's right. So the way that I explained the greedy algorithm, it seems to be very memory inefficient, because the way it's stated says, okay, you have to look at all the previous guys and check if something is already there or not. Mm-hmm. This somehow defect can be easily remedied and removed. You can make it very memory efficient, that you don't need to store anything, but just the last permutation and some extra data structures that prevents you looking up anything.
I see.
So this can be done. I didn't explain what, but
and,
yes.
And can a similar thing be done in the generality of these?
If you, yeah, that's a very good question. So this greedy algorithm, if you translate it to these hyperplanes, these supersolvable arrangements, the greedy rule is you start at the canonical base region, and then when you look at the hyperplanes that are around you, and you try to go through one that is an H1. This is the highest priority. If you can go through one of H1, you do it. If you can't, and entering a region that is new, that you haven't seen yet. If you can't, then you go to one of H0. And which one? You then determine recursively from H0, because H0 is again supersolvable, so again you do this, but yeah.
Thank you.
So the greedy rule says, always go through the red ones, the H1, if you can, and if not, then take a blue one. Yeah.
Thank you.
Any other question?
So for this type B, or what was it, sine graphs, so the sine graphical zonotopes, you characterize those which are supersolvable. Have you looked at which ones gives lattices? So there's this in type A, I have this characterization of which are lattices. I'm sure that this characterization you can make it in type B.
I'm not sure. Do you know this, John? I don't know the answer.
Supersolvability implies that there's lattice, but there could be more like
yes.
in type A. Yeah,
there will be much more.
This remains to be done.
Yes.
Mm-hmm. Mm-hmm.
And then if you have that, then you had this question whether this would be, I mean, whether you can realize the quotientopes in this.
Yes.
Then, I mean, with the same path, you will use the type B shard polytopes.
Okay.
Even for the arrangement, the graphic arrangement in type B, even for it to be supersolvable, the condition is a bit more involved. Like the if and only if is a bit more than what was on the slide, and it's already a bit intricate, just for supersolvability.
Aha.
Right, like you mentioned it. Any other question? No? Okay, so let's thank the speaker again.
Thank you.
And